afternoon. It is a great honor to present to you today. My name is Liu Xinyu, and I'm here to discuss our recent work titled Multi-level Graph Convolutional Networks with Enhanced Partitioning Strategies for Skeleton-based Action Recognition. I divide my presentation into 4 parts: introduction, related work, methodology, and experiments. First of all, I will introduce the background and significance of this topic. Human action recognition from video data is becoming increasingly important, with applications in video surveillances, healthcare, human-computer interaction, and industry and logistics. The skeletal representation is resilient to variations in appearance, lighting, and background, making it more adaptable to real-world conditions compared to the traditional video-based methods. As the technology advances, skeleton-based methods play an increasingly important role in action recognition. Now, let's move on to the related work. st-gcn, which first used GCN in this field. The human body joints are taken as the vertices of the graph structure, and the physical connections between the joints are taken as the edges. And the same joints in different frames are connected to construct the graph in spatial and temporal dimensions. Later, some people improved st-gcn and proposed the 2-st-gcn model. A two-stream network was introduced, and an adaptive graph convolutional network was proposed, which can be better adapted to the action recognition task and the hierarchical structure of GCNs. However, there are still some limitations. First, overlooking non-physically connected joint interactions. Second, limited ability to capture the temporal region-wide dependencies. Next, I will introduce how I improve it. Our work introduces several key contributions that I would like to highlight. First, we propose 3 improved partitioning strategies, including multi-level partitioning, symmetric hand-head interaction partitioning, part-based partitioning. Second, we incorporate a multi-level graph convolutional network, where multiple adjacency matrices of different levels are used for graph convolution separately. Finally, we introduce a temporal convolutional network with a non-local block to better model long-range temporal dependencies. This is the overall process of the system. Let's focus on the structure of ML-GCN network. ML-GCN layer extracts spatial dependencies from adjacent joints, and ML-GCN layer extracts temporal dependencies globally from consecutive frames. Let's go to the first contribution. We have designed 3 different strategies. The first is multi-level partitioning strategy. Human actions vary greatly in their execution. from those requiring extensive movement of the entire body to those involving minimum localized movement of a single body part. This diversity highlights the limitations of traditional strategies in connecting distant joints and recognizing actions across a broad spectrum of amplitudes. To solve this problem, we designed different levels of the human skeleton. Level 0 is the original graph. Level 1 shows the structure with the largest node span, followed by level 2. The second is symmetric hand-head interaction partitioning. We observed that the majority of actions in the datasets exhibit symmetry and often involve interactions between hand and head joints. So we devised a strategy to enhance spatial configuration partitioning by incorporating symmetric and hand-head connections. The third is part-based partitioning. It is known that most of the actions involve interaction between different body parts, so we divide the human skeleton into 3 categories: trunk, arm, and leg, as shown in this slide. According to the description of multi-level partitioning strategy, we have proposed 3 different hierarchical graph structures. To better utilize these graphs, we design a separate adjacency matrix for each graph, which makes the extracted spatial features richer. The spatial convolutional network in the st-gcn model uses a single adjacency matrix A, while we designed 3 different structures of adjacency matrices A0, A1, and A2, based on the different levels. Since st-gcn uses a standard GCN structure, while 2st-gcn employs an adaptive graph convolutional network, we design distinct network structure for each baseline. Based on the st-gcn, the structure of multi-level graph convolutional layer is shown in this slide. And this one is the structure of multi-level graph convolutional layer based on 2st-gcn. Video sequences usually contain rich spatio-temporal information, in which the contextual information of the actions may be far apart in time. This requires model to be able to simultaneously capture local feature information and understand the global dependencies in the entire video sequence. Therefore, we use the non-local block, which is a mechanism for capturing long-distance dependencies in the video sequence, and can aggregate the information over a large range, rather than just relying on local information. The structure of non-local temporal convolutional layer is illustrated in this figure. In this part, I will experimentally validate the effectiveness of our proposed method. To explore the optimal strategy for enhancing recognition performance, we conducted comparative experiment across two datasets using two baseline models. Left table shows the results of st-gcn using our proposed three strategies, while right table shows the results of two st-gcn. This experiment underscores the indispensability of the three strategies, as each demonstrates suitability for different benchmarks and datasets. We conduct detailed ablation experiments, as the table shows. When combining these three approaches, the model achieves 96.9%, surpassing the baseline by 1.8%. To ascertain the effectiveness of our proposed ML-GCN model, we compared its performance with several popular methods. According to these two tables, our proposed ML-GCN have a certain elevation in accuracies compared to these methods. Through these experiments, our model showed promising results on NTU-RGB+D and Kinetics datasets. Looking ahead, our future research will explore the integration of more dynamic partitioning mechanisms and the application of these models to a broader range of activities, potentially revealing novel perspectives on recognizing complex human actions. That's all. Thank you.